Hello friends. In this video, we will take a look at the popular and relatively budget-friendly FCHAO inverter designed to operate from a 12-volt battery and with a declared power output of 2000 watts. We will look at the package contents, take it apart, and run a series of tests, from checking the sine wave shape to testing maximum power and long-term operation under heavy load. By the way, in this part of the review, we will test the real capacity of the Humsienk lithium iron phosphate battery rated at 320 amp-hours, which I promised to test in its review. The link is in the description below the video. And we will assemble a complete system consisting of the inverter, the battery, and a 60-amp charger, thus getting a powerful 2 kilowatts uninterruptible power supply with a capacity of 4 kilowatt-hours of energy. It can be used both on a permanent basis and as a backup power system in case of a power outage. And before we begin, as usual, I ask you to like this video. This will help other people interested in this topic find it. And subscribe to my channel if you have not done so before. The main hero of this review is the inverter. There is a separate video about the battery. The link is in the description. An important point, it cannot charge. Its task is to convert the battery's direct voltage into alternating mains voltage at the output. This model is designed for an input voltage of 12 volts, with a declared power of 2000 watts. Of course, for such power, if possible, it is better to choose a higher voltage version, 24 or 48 volts, because at 12 volts the input currents become very large. But in my case, I am limited by the 12-volt battery I already have. The manufacturer declares a pure sine wave and a standard set of protections: reverse polarity, overheating, overload, low and high input voltage, as well as short circuit protection. The body dimensions are 38 by 23.3 by 9.6 centimeters, and the weight is about 3.4 kilograms. Delivery turned out to be quite long, more than a month and a half. At some stages, the parcel simply stalled for 2 weeks or more without any noticeable movement. As a result, the inverter arrived at a regular post office. The box is simple, without any additional outer protection, but judging by its appearance, nothing critical happened to it. There are no strong dents or visible impact marks. The box is universal, intended for different inverter versions, with a pure or modified sine wave, with different input voltages, different power ratings, and different output voltage options. But in my case, none of the items are marked. I hope the store did not mix anything up. The inverter is secured by 2 foam inserts on the sides and is additionally packed in a bag. The manual is visible on top, and behind it the power cables for connecting to the battery are laid out. Nothing is loose inside the box, and everything arrived without visible damage. The package includes the inverter itself, 2 pairs of power cables for connecting to the battery, a remote display, a cable for connecting it, and a small manual. The power cables here are not one thick pair, but 2 parallel pairs of equal length. They must be connected together. This way the current is distributed between the wires, and the cables themselves remain more flexible and easier to route. Separately, the package includes a remote display with a power button and a long connection cable. It can be installed separately from the inverter, for example, on a panel or in a more accessible place if the inverter itself is hidden near the battery. There is a warning on the display housing. When using the external display, the main switch on the inverter itself must be turned off. That is, control in this case is transferred here to the remote module. For stationary installation, this is a convenient solution. There is no need to reach the inverter itself every time to check parameters or turn the device on. The device housing is metal with massive ribbing that works as additional heat dissipation. There are plastic covers on the sides, and mounting pads are provided on the bottom for stationary installation. On the front side, there are a European socket, a built-in display, a power button, LED indicators, and a connector for the remote display. In my version, there is 1 socket, but more powerful models have 2. This is worth paying attention to when ordering, because the versions differ not only in power but also in socket type: European, British, Australian, or universal. On the rear side, there are ventilation grills of the cooling system. Fans are installed behind them. The power terminals for connecting the battery are also located here. The terminals are large, with clear polarity markings, and are additionally covered with plastic protective caps. For a 12-volt, 2-kilowatt inverter, this is an important point. The currents here are high, so an accidental short circuit at the input can be very unpleasant. The battery cables are connected through threaded studs with nuts. The polarity is duplicated both by color and by markings on the housing. Black is minus, red is plus. For a 12-volt, 2-kilowatt inverter, this is one of the most important units, because the input currents here can be very large. Therefore, both pairs of included wires must be connected in parallel, the contact pads must fit tightly, and the nuts must be properly tightened. On the bottom side, on both edges, mounting tabs are installed, so the inverter can be properly fixed, for example on a wall, rather than simply left lying next to the battery. The inverter is disassembled quite easily. You need to unscrew the screws from the front and rear plastic covers, after which they can be removed, and the upper half of the metal housing can be opened. The housing itself consists of two parts, and the inverter board is fixed to the lower half. I did not remove it completely. For a general inspection of the component base, this is enough. The production date is visible on the heatsink, March 11, 2026. The main power components are pressed against the aluminum heatsink with metal bars. Some of the elements are covered by the fasteners, so the markings cannot be read without full disassembly. The layout shows several parallel groups of power switches. For a 12-volt, 2-kilowatt inverter, this is expected. The input currents are high, and they need to be distributed among several elements. Inside, the layout is dense, but the main assemblies are clearly distinguishable. In the center there are transformers and large capacitors. On the right is the output filter choke, and along the lower part a row of power switches on the heatsink is visible. Cooling is active. Two fans are mounted on the rear panel for exhaust, plus a separate small fan is installed above near the power section. In general, the circuit is typical for an inverter of this power. First a step-up DC-DC converter, then AC voltage generation and output filtering. A close-up of the fans on the rear panel. Nearby are the battery input terminals, and it is clearly visible that 3 wires go inside from each of them. For a 12-volt system, this is logical. The currents are large, so they are distributed among several conductors in order to reduce the load on each individual wire. On the front side, a separate control and indication board is visible. The display, button, indicators, and external screen connector are connected to it. On the right, there is the socket. AC power wires go to it, and a protective conductor is connected separately. Nearby, there is a small fan and a large output filter choke. Overall, the assembly is neat. The connections are on connectors. The wires are routed without tension, and I did not notice any signs of careless soldering or unclean flux. In one of my previous videos, I already talked about the Humsienk lithium iron phosphate battery rated at 12 volts and 320 amp hours. Back then I mentioned that I was waiting for an inverter for it, and this is exactly that inverter. In the same video, I also showed the charger for this battery. As a result, everything together turns into something like a simple charging station, a battery, a charger, and an inverter with a declared output power of 2000 watts. The battery capacity is declared at about 4 kilowatt hours, but in the previous review, I did not fully test it. At that time, there was no suitable load. So in this video, we will test not only the inverter itself, but also see how much energy this battery will actually deliver under prolonged load. The connection turned out as follows. 2 pairs of power cables, the ones that came with it, run from the battery to the inverter. Separately, another pair of wires from the charger, which lies on top of the inverter, is connected to the battery. For convenience, I tightened them with plastic ties so that they would not spread apart and create extra load on the terminals. As a result, I got a simple homemade charging station, battery, charger, and inverter in one bundle. First, power up. On the inverter screen, the battery input voltage is shown on the left, currently 13.5 volts. In the center, there is a conditional charge indicator. The battery is recognized as fully charged. On the right, we see the output voltage, 233 volts. No load is connected yet, so the output power is 0 watts. At the bottom, the temperature of the power section is displayed. At startup, it is 21 degrees. The remote display is connected with the included cable directly to the connector on the front panel. After connection, it fully duplicates the built-in display. Input voltage, output voltage, current power, and temperature. It can also be used to control the inverter on and off. But for this, the main switch on the housing must be turned off. Test startup, a hair dryer as the load, with power close to 1 kilowatt. The inverter immediately turns on forced cooling. Its icon is visible on the left side of the screen. But since the temperature will not have time to rise much, the cooling will turn off immediately after the hair dryer is switched off. The next important test is checking the shape of the output signal. For this, I assembled a small test bench with a pocket oscilloscope and a step-down transformer. The transformer is needed here for safe direct connection of the oscilloscope to the mains. It does not distort the signal shape, but allows the oscillogram to be recorded correctly. First, for comparison, I looked at the regular city power grid. This is how it looks live. The multimeter shows the secondary winding voltage and the mains frequency, 50 Hz. The sine wave is moving. I was not aiming for full synchronization. I only care about the signal shape itself. Now I connect this same test bench to the inverter output. I make the first measurement without any additional load. In fact, the inverter is now operating almost at idle. I do not see any differences from the measurements on the city grid. The sine wave has the correct shape. The mains frequency is 50 Hz. Everything is fine. Now let us complicate the situation a little and take measurements under load. And I decided not to do this halfway, but to load it seriously, using a heater for that. The power is 1,375 watts. Here the constant forced cooling is already running. Although at the start the temperature is still low, 24 degrees. This practically did not affect the sine wave shape. If you look very closely, you can see a slight unevenness on the wave, but it is minimal. The frequency is normal. Overall, everything is fine. Separately, a couple of words about charging. A charger with a maximum current of up to 60 amps is used here. It was already shown in the review of this battery and the smaller 1 kilowatt-hour version. In this case, I limited the charging current to 50 amps. The charger is connected directly to the battery and can operate simultaneously with the inverter. If the inverter consumption on the 12-volt side is less than these 50 amps, the remaining current goes to charging the battery. If the load is higher, then part of the energy comes from the charger and the missing part is taken from the battery. Now we move on to checking the maximum load. The declared power of the inverter is 2000 watts, so let us try to approach this value in real conditions. The main load will be a smart electric kettle with a power of about 1800 watts. Its review was on my channel not so long ago. The link is in the description. To get closer to 2 kilowatts, I added a few more consumers, a charging station, and a light bulb. Right now, without the kettle, the load at the inverter output is slightly more than 200 watts. I turn on the kettle. Forced cooling turns on immediately. At first, the total power is more than 2100 watts. Then it drops to about 2040 watts, exactly 1800 watts from the kettle plus the additional load. Next, I will speed up this video so that you do not have to wait. In reality, it lasts 4 minutes. During this time, the wires from the battery to the inverter became quite noticeably warm. When the kettle starts boiling, the power drops sharply by more than half. The test was passed successfully, even at a higher power than was declared. Now let us move on to testing the real capacity of the Humsienk battery rated at 12 volts and 320 amp hours, which I promised to do in its review. Let me remind you that it has a BMS with Bluetooth that integrates into Home Assistant. Before starting the test, I charged it to 100%. At the inverter output, I installed a Sonoff S60 socket with an energy monitoring function. You will also find a review of it in the description below the video. Unlike similar sockets, which have only one common energy sensor, This one has 4. From top to bottom, total, yesterday, today, and the current month. Here is the test bench ready for long-term discharge. As a load, I will use the heater, the same one as in the sine wave measurement under load. In this test, it is important to separate the internal, that is the real battery capacity, from the useful one, the one it can deliver through the inverter. What I mean is that the power the battery is currently delivering according to the BMS measurements is a little over 1,600 watts, with a current of almost 120 amps. But at the output, according to the socket measurements, it is 1,366 watts, a little over 6 amps. The difference is the conversion of direct current into alternating current and stepping up from 12 to 230 volts. This consumes about 20%. We will take this coefficient into account in the further measurements. The inverter readings, 1375 watts, practically match the socket readings. That is, at the output we will get the energy delivered by the battery through the inverter, converted, but taking the losses into account, it will be about 20% lower than the internal energy, what the battery actually delivered. The first intermediate check, according to the socket readings, the battery has already delivered 1150 watt-hours of energy, which in terms of pure internal battery energy, is about 1360 watt-hours. The charge level is 66%. The power has practically not changed all this time. Cooling is running constantly. The inverter temperature is 41 degrees. The battery voltage according to the BMS is 13 volts, and according to the inverter it is 12.1. The next check, at the mark of 2 kilowatt-hours of delivered energy, according to the socket data, which in terms of the battery's internal energy is about 2,370 watt-hours. The charge level is 42%. The voltage dropped by 1/10 of a volt, both according to the BMS and according to the inverter. Due to the cooling, the inverter temperature dropped slightly to 38 degrees. We are approaching the end of the test. The charge level is 12%, and 3 kilowatt-hours of energy have been delivered through the socket. This is about 3,585 watt-hours directly from the cells. The voltage on the BMS is 12.6 volts. On the inverter, 11.6 volts. The temperature rose slightly to 39 degrees. The BMS disconnected the battery when the inverter showed a voltage of 9.6 volts, which means about 10.6 volts on the BMS, as in this screenshot. Without a connected load, there is no sag, and the voltage values on the inverter and the BMS are almost equal. The battery was able to deliver 3,360 watt-hours of energy through the socket, which in terms of internal energy is just over 4,000 watt-hours, which practically matches the declared value. And that is considering that the discharge was carried out at a current above 120 amps. But once again, I want to emphasize that these 4 kilowatt-hours are the internal energy of the battery. When used together with the inverter, the conversion losses amounted to about 20% of the useful energy. Without load, the inverter was able to start, although the battery showed a 0% charge level. Even the cooling fans worked for some time, until its temperature dropped. According to the BMS, active ventilation consumes about 20 watts. One more observation when using it as a backup power source for low power loads, up to 200 to 300 watts. Most of the time, the inverter operates silently, but the screen shows that the temperature is gradually rising. The higher the load and the ambient temperature, the faster the inverter temperature rises. At 45 degrees, cooling turns on, quickly lowers it to 40 degrees in about a minute, and turns off. With a load like in this photo, and a room temperature of 22 degrees, it turned on for a minute on average once every hour to hour and a half. The inverter pleased me. Unlike cheaper models with some outrageous figures of 5 to 6 kilowatts written on them, but in reality starting to smoke at loads of 500 watts and above, here all the figures fully correspond to reality. It really holds its 2 kilowatts and can operate for a long time with such loads. The solution with the remote display is also very convenient. It can be installed somewhere close at hand while hiding the main unit. I also like that the active cooling system does not run constantly without stopping, but activates only when necessary. With small loads, it operates silently almost all the time. The only thing I could add is that if you plan to use it at near maximum loads, around 2 kilowatts, for a long time, I would either replace the battery wires with even thicker ones or add 1 or 2 more pairs. In the kettle test, they became quite noticeably warm. But in the heater test at 1.3 kilowatts over several hours, they remained simply well warm. The battery test also showed that the real parameters matched the declared ones despite the high discharge current, which is also a good test in itself. Long-term operation for several hours with a powerful load of more than 120 amps. Overall, I achieved the task I had set, to get a backup power unit with enough power to run an electric kettle, a microwave oven, an electric grill, and with a capacity of 4 kilowatts. Perhaps it is worth thinking about a more powerful charger. We will see. That is all. I hope the video was useful and interesting for you. I would appreciate a like. It helps promote the video on YouTube. If you have not yet subscribed to the channel, now is the right time to do it. In the description below the video, I will leave links to all the devices and the reviews mentioned, as well as my social networks, Telegram channel, and the group for discussing smart home topics. Join in, it will be interesting. Thank you for your attention. See you next time. Peace to everyone.